Greetings and welcome to Distillate. So, today we are going to talk about boundary value problems. So far we have discussed ordinary differential equations of the form this, right? So, we have discussed ordinary differential equations of this form. So, these are either ODEs, a single ODE or a system of ODEs, and or basically a higher order ODE could be reduced to this form and so on and so forth. So we can definitely solve such problems, but these problems, the requirement for us to solve these problems by the methods that we learned before is that we have a condition at t equals to 0. So if we know the value of the function, let's say, the value of the dependent variable y at initial time. So let's say we have this condition, which is the initial value. So if we have this information, we can definitely solve this problem using methods that we've learned so far. However, it is not necessary that we always have problems where the initial value is known, or it is not necessary that we always have problems where just the initial value is known. So, for example, you could consider, let's say, the problem of diffusion in a cylindrical pore, right? So, diffusion in a cylindrical porous catalyst. So, in this case, you use, let's say, this is over here, the Z direction, and this is, of course, R, right? And let's say everything is spread uniformly in R, but in Z it is not. So if you write a governing equation for this, so that is basically diffusion, convection, and reaction. So these three are taking place together. These three scenarios are happening together. So there is diffusion, there is convection, and there is reaction, right? So all of this is happening, and let's not consider a first order reaction. Let's take a generalized case a to the power n, right? So that is the idea over here, and now we are going to try and solve for the concentration profile, right? So let's say this is the problem that we have. Okay, now in such problems, usually we know information at the start, so we'll know the information at z equals to 0, but we also have some information about z equals to L. Okay, so these two, z equals to 0 and z equals to L, both are boundaries. Okay, both are boundaries, and information at these two boundaries are known as boundary conditions. Okay, so we have boundary conditions at both z equals to 0 and z equals to L. And this is a second order ordinary differential equation. So we'll need two boundary conditions. So generally it goes by assigning one condition at z equals to 0 and one at z equals to L. You can definitely have two conditions at z equals to 0, but usually we are not able to assign as many conditions at a single boundary. So the most physically relevant conditions that people do assign is that we fix the concentration at the preceding end. So sorry, the start. So we basically say that CA is fixed at this end, which is, let's say, CA naught, right? And that is just fixed by the bulk mass transfer over here. Okay, but in the in the pore itself, there is going to be reaction of Ca. So it is going to the concentration of Ca is going to change because of these three effects that we have underlined in the in the differential equation, right? And finally, at the end, that is at z equals to L, there is no reaction taking place because now the catalyst is no more here. So at this end of the pore, we assign a no flux condition. So basically dCA by dz is equal to 0. So these are the most physically relevant conditions. Okay, these are physically the most relevant. So we have a fixed concentration condition at z equals to 0 and a no flux condition at z equals to L, right? So these are physically very relevant, but now we have conditions at two different boundaries, and this kind of a problem cannot be solved using the initial value methods for initial value problems that we learned so far, right? So we'll have to apply a different set of methods to solve problems over here, right? So in this lecture, we'll learn how to treat such problems. We'll learn a method called finite difference method to solve such problems. We'll also learn how to deal with different kinds of boundary conditions. And in the subsequent lectures, we'll try to solve some problems which deal with such cases, right? So hopefully in the next few lectures and tutorials, we will be well versed with dealing with such problems. Okay, so let's start with the method of finite differences. So the finite difference methods. Okay, so that's what we are going to learn today. So we have already had an introduction to finite differences when we did numerical differentiation. So we basically said that let's say we have to get the derivative at a given point, right? If we need to do that. So there are three ways to do this. One is a forward difference method, where you use the point ahead and the current point, right? And by the way, delta x in this case is just xi plus 1 minus xi, right? Or you use a backward difference method, which is yi minus 1. So basically use the point, the current point and the point behind it, okay? And over here, delta x is just xi minus 1, right? And there is centered difference method where you use the point ahead and the point behind, right? And over here, delta x is just xi plus 1 minus xi, which is also the same as xi minus 1, right? So here we sort of assume a constant delta x, right? So these are the three methods that we learned for evaluating a derivative. And over here, we also showed that these two methods are first order accurate, but this center difference method is second order accurate. So generally, when we develop techniques for finite differences, we use the center difference method because that is more accurate, and overall it increases the order of accuracy of your solution, right? So we'll be using the second order accurate methods. So let's try to do the same for double derivatives. So double derivative at a given point so double derivative at a given point is, so the formula that we'll be using is okay upon delta x squared. Okay, so that is what we use for double derivative. And for a single derivative or the first derivative, we will be using the center difference formula. Okay, so these are the two formulas that we'll be using. You can definitely go to higher order derivatives as well for more complex higher order ODEs. But most of the ODEs that I have come across in chemical engineering are just second order. The maximum order is second order. So you won't really have to worry much about ODEs of a higher order. And you could also simplify ODEs of higher order. So that should not be much of a problem. So we'll deal mostly with second order differential equations, right? So now that we have this, let's try to discretize our entire domain over here, right? So let's try to solve the same equation that we had shown over here. So that was diffusion, convection, and reaction, right? This is the equation that we are going to try and solve. And now we have to discretize this. So remember, we have our domain from z equals to 0 to z equals to L. Okay. So this over here, this point over here, this is going to be the first point. So z naught. And this is going to be the last point. So that is Zn. So in total, you will have n plus 1 discrete points. Okay. So you will have in total of n plus 1 discrete points when you are dealing with this kind of a problem, right? And further, when you have these discrete points, you will definitely have these points here. So this is Z1, Z2, Z3, and so on. So these n plus 1 discrete points are going to divide your entire interval into n intervals, right? So these are going to be n intervals. So that's the thing. Okay. And since we are equally spacing the points currently, so I'll just write it down over here. These are equally spaced, right? And since we are discretizing them into equally spaced points, the n intervals, each of them will have the length as delta z in this case. So let's use z. So delta z, which is going to be the step size basically when you move from zi to zi plus 1, right? And therefore, if we have n intervals of delta z step size, so the total length is going to be n times delta z, and that is just L. So that gives you delta z as L over n. Okay. So this is something, this seems to be very trivial, but at times I have seen people getting very confused about these things. So if you have n plus 1 discrete points, including the points at the boundaries, you will have n intervals into which they'll split it. And that gives you your step size as L over n, where L is the length of each step, right? This over here is a one-dimensional ordinary differential equation. So it just has one direction, which is z. But let's say you go to solving partial differential equations, which we will do later on. So we'll see there are two or multiple directions involved. So let's say there's L is the dimension in the z direction, and let's say h is the dimension in another direction, let's say y direction. So in that case, you will have a different step size for z direction, which would be L by n, and a different one for y direction, which would be h by n, right? Or you would have different number of points. So yeah, this is a very important thing to know. So this basically gives us the step size. Okay. So now we have fixed our step size. Okay. So step size is fixed for us. These discrete points are fixed. So this is Z1, Z2, Z3, and so on. So this is Zn minus 1, and this is Zn, right? So now let's just discretize this. So if we discretize this, we'll get d ci plus 1 plus ci minus 1 minus 2ci over delta z squared. That's the second order, second derivative formula that we've used. Okay. Then let's discretize this term over here. So that's going to be minus v ci plus 1 minus ci minus 1 over 2 delta z. And then this is just kci. Okay. So we have written down this equation. We have discretized this equation at z equals to zi, right? That is what we've done. Okay. Now, clearly, your I goes from 0 to n, right? So that implies there are n plus 1 values of I. Okay. There are n plus 1 possible values that I could take, right? For each zi, there could be a discretized equation like this, right? For each zi, there could be a discretized equation like this. So therefore, there are going to be n plus 1 equations. Okay. So there are n plus 1 equations because of n plus 1 values of I. Hopefully that makes sense to all of you. But if you look at the boundaries, that is, if you look at I equals to 0, so when we look at then the equation here becomes d c1 plus c minus 1 minus 2c0 upon delta z squared minus v c1 minus c minus 1 minus 1 is the subscript, right? So upon delta z, 2 delta z plus k c0 equals to 0, right? Now over here, you see c minus 1, right? So we see something as c minus 1 over here at 2 places. And c minus 1 is basically c at z minus 1, right? So c minus 1 would just be c defined at z at minus 1. But z starts from z0. So this is not defined, right? This is not defined. So that means these two circles over here, these are not defined. Okay. So that is the first problem. So that makes this equation invalid, right? So this is an invalid equation because two of the terms here are not really defined, right? So that reduces our number of equations to n, right? Now let's see the other boundary, which is I equals to n. So when we do that, we see D Cn plus 1 plus Cn minus 1 minus 2Cn over delta Z squared minus V Cn plus 1 minus Cn minus 1 over 2 delta Z plus Kcn is equal to 0, right? So when we do this, once again, we see Cn plus 1, right? Cn plus 1. This is once again not defined, right? This is not defined. So this equation becomes invalid as well, right? This equation becomes invalid as well. And therefore, the total number of equations that we have now are n minus 1, right? Let's go back to our domain over here. So we have Z0, Z1, Z2, and so on till Zn. And we have concentrations defined at each of these points. So we most certainly have n plus 1 variables because n plus 1 different values of concentrations. But we have just n minus 1 equations. So we have n minus 1 equations because two of the equations at the boundaries have been invalid. And we have n plus 1 variables. So this means we need two additional equations, right? We need two additional equations. So now let's break the suspense. Now to get those two additional equations, we go to the two boundary conditions. Okay. We go to the two boundary conditions at z equals to 0 and z equals to L, or at z0 and zn, right? So basically when I is equal to 0, we'll use the first boundary condition, and when I equals to n, we'll use the second boundary condition, right? So these are the two equations that we get. So now let's see how to deal with boundary conditions. Okay. So let's try to deal with boundary conditions. So before we go on to deal with boundary conditions, let's see what all types of boundary conditions can we expect to see. So the three commonly seen boundary conditions are are the Dirichlet boundary condition, all right. So they are the Dirichlet boundary conditions. So the Dirichlet boundary conditions are basically where the value of the dependent variable is specified, okay, at the boundary. So for example, in our problem, this over here is a Dirichlet boundary condition because the value is specified, okay. The second kind of boundary condition is a Neumann boundary condition. So Neumann boundary condition or a Newman boundary condition. So in the Newman boundary condition, the derivative is specified. Let's say it's some value, right? So the derivative is known, okay? And the third, so for example, in our problem, this side is a Neumann boundary condition. So derivative is 0, right? So this is specified, okay? Let's actually call it, let's not call it D, let's call it C. Let's not call it C naught either. Let's call it B1 and let's call it B2, okay? And after that, there could be a mixed boundary condition where you have a combination of the Neumann and the Dirichlet boundary condition. So something like this could be a mixed boundary condition, right? So we'll see how to deal with the Dirichlet and Neumann boundary condition, and then you will automatically know how to deal with the mixed boundary condition. Okay. So when it's a Dirichlet boundary condition, it actually is a simpler case because um, this adds as an additional equation. Okay. So this acts as an additional equation. So this itself acts as an additional equation. So you don't really need to worry about uh, just treating it differently. So for example, over here, our n+1 variables include the variables from C0 to Cn, right? So one of the variables actually gets cancelled out because it is already known, right? That value is already known. So this reflects in the equation at I equals to 1. So when we'll solve this problem, I'll actually show you how this reflects in the I equals to 1 equation. But this dealing with Dirichlet boundary condition is not a very big problem, right? Neumann boundary condition can be a bit challenging. Okay, so let's see how to deal with the Neumann boundary condition. So let's say the Neumann boundary condition is at a given boundary. It could be a left boundary or a right boundary, whatever. So let's say it is at the left boundary. Okay, so which means you have this Z0 over here, Z1 over here, and so on, right? And there's a Neumann boundary condition here. Okay, there's a Neumann boundary condition at this boundary. Okay, so whenever dealing with a Neumann boundary condition or a boundary condition having derivatives, what we do is we consider what is called as a fictitious point. Okay, so what we do is we use a fictitious point to solve such problems. So a fictitious point would mean we will assume that towards the left of Z0, there's a fictitious point Z minus 1. Okay. And there the concentration is defined as C minus 1. Okay. Now, this adds an additional variable, right? This adds an additional variable, but that additional variable also gives you an additional equation which is at I equals to 0. Okay, so you could write an equation for I equals to 0 which earlier was invalid because C minus 1 was not defined. So now since we've defined this fictitious point, we have an additional equation, right? So what we did over here is that we added a variable. So now we have a total of once again n+2 variables, right? And since now we have considered one of the equations valid, so now we have now we have n equations altogether. Okay, so still we need two additional equations, and one equation we'll get from here, right? So one additional equation that we get from this is that dc by dz at z equals to z0 is constant. So therefore, if you apply a finite difference over here, you will get c at minus 1. Sorry, c at 1, which is the next point, minus c at minus 1, which is the previous point, divided by 2 delta z is equal to a constant. So this acts as an additional equation. So this has again two variables, C1 and C minus 1. And now C minus 1 is a defined variable. It's not invalid anymore, right? So this becomes an additional equation. So because of that, now you have n plus 1 equations. And the next equation comes from the other boundary, right? And similarly, if you have, um, let's say in both the at both the boundaries you have a Dirichlet, a Neumann. So let's say the right boundary, which is Zn, also has a Neumann boundary condition. So over here we have Zn minus 1, and here we could consider a fictitious point Zn plus 1, and dc by dz at Zn is, let's say, capital B2, just saying, right? So once again, we have added a variable Cn plus 1, right? So now we have got n plus 3 variables, right? And we so far had n plus 1 equations. But once again, since we've defined Cn plus 1, now the equation at n is no more invalid. Okay. So we have added another equation, which is this equation, right? This equation has been added. So now there are n plus 2 equations, and the last equation comes from this. So we say dc by dz at Zn is B2, which gives you Cn plus 1, which is now defined, minus Cn minus 1 over 2 delta Z is equal to capital B2. This is an additional equation. So we already had n plus 1 equation because of this boundary condition. We added a fictitious point, increasing the number of variables. So we have n plus 3 variables, n plus 1 equations. Then, because we've defined Cn plus 1, now the equation at n is not really undefined. So we added another equation because of that. So that makes it n plus 2 equations. And finally, we applied the finite difference here. That gives you additional equations. So now we have n plus 3 equations. So we have n plus 3 variables, we have n plus 3 equations, and therefore the problem is now solved, right? Now this problem can be uniquely solved. Okay. If you have a mixed boundary condition, you could treat it the same way because it has a derivative here, right? So all that you need to do in that case is that, let's say there's a mixed boundary condition at, let's say, the left boundary. So let's say this is Z0, this is Z1. So since there is a derivative in the boundary condition, you absolutely have to define a fictitious point. So that is going to be Z minus 1. Okay. Here it's going to be C minus 1, here C naught, and here C1. All right. And over here we have the mixed boundary condition, or I think I had this alpha C plus beta dc by dz equals to 0. So now the equation that you're going to formulate is going to be alpha C naught plus beta C1 minus C minus 1 by delta Z is equal to, let's say, a constant. So B3. So B3, right? So this acts as an additional equation, right? So this can be solved as well. So anytime you see a derivative in the boundary condition, you have to use a fictitious point, right? So that is it. If you have a Dirichlet boundary condition, it is fairly simple because you just have to use the value over there. Okay. So now that you have a fair idea of dealing with boundary conditions, now let's try and solve the problem. So the problem where we left it, we had n plus 1 equations, but 2 of them were invalid. So we had n plus 1 variables. We had n plus 1 variables, but n minus 1 equations. That was the problem that we had left. And now we have to apply our boundary conditions over here. So let's look for additional equations in our problem. Okay. So additional 2 equations in a problem. So let's start with the left boundary. So when we talk about I equals to 0, so now we actually have at I equals to 0, C naught is known, and that's a constant, right? C naught is known to be a constant, right? So this actually becomes an additional equation here. Okay. So there are two ways that you can deal with this. You could either say that we have n plus 1 variables, and this is an additional one equation, right? So that means this acts as an additional equation. Or you could modify the equation at I equals to 1. So that's the second thing that you can do. So if you write the equation at I equals to 1, so the equation at I equals to 1 is just d C2 plus C0 minus 2C1 upon delta Z squared minus V C1, VC2 minus C0 upon delta Z plus K C1 equals to 0. That's the equation at I equals to 1, right? So now what you know is that this value is known to be a constant, right? This value is known to be a constant. So you could just modify this equation. So you could write this as d C2 minus 2C1 by delta Z squared minus VC2 by delta Z plus KC1 is equal to, let's see, minus dCA naught by delta Z squared and minus VCA naught by delta Z, right? So now you have the LHS, which has variables, and the RHS, which is just a constant, right? So you can modify the equation over here. Now, the point of this modification is that now all of the equations have just n variables starting from C1. So you have C1 to Cn, right? So you have just n variables. You've eliminated a variable. So you could do either cases. So you could either treat this as an additional equation and keep treating C naught as a variable. That works as well. Or you could reduce an equation and simplify your problem further before writing it down into a matrix. Any way works. So this is how you could treat a Dirichlet boundary condition. Okay. So that hopefully is clear. And now we'll deal with the Neumann boundary condition. So the Neumann boundary condition is at the other end. So let's deal with that. So at I equals to n, as we said, that we'll introduce a fictitious point. So this is our domain right here. So let's introduce a fictitious point Zn plus 1. And now because of that, this equation that we wrote at I equals to n, this is no more invalid. Okay. So this is not invalid anymore. So we'll have an additional equation at I equals to n. So that would be d Cn plus 1 plus Cn minus 1 minus 2Cn over delta Z squared minus V Cn plus 1 minus Cn minus 1 over delta Z plus Kcn equals to 0. So that is an additional equation, right? And there's also an additional variable. Okay. So we have n plus 1 variables now, if you consider eliminating C naught as a variable. So you have n plus 1 variables, right? You started with n minus 1 equations, and now there's this additional equation. So you have n equations, right? And let's add the Dirichlet boundary condition. Sorry, the Neumann boundary condition. So dc by dz at zn is just 0. So that means cn plus 1 minus cn minus 1 by delta z is equal to 0. That's the additional equation, right? So that is another equation. So now you have n plus 1 equations. So you have n equation, you have n plus 1 variables, you have n plus 1 equations, right? So now it is just very easy to solve this kind of a problem. So uh, we can write this in the form of ax equals to b, right? And this type of a problem we can very easily solve using Python, right? So whenever you discretize anything, all that you have to worry about is making the matrix A and the vector B. And once you get that, it's fairly simple, right? So now that we've discretized all the equations, let's now try to formulate this matrix. So the matrix A is the biggest challenge over here. So I generally prefer to make simplifications before going ahead and making the matrix. So that is why I would choose this method over here, where I eliminate the variable C0. Okay. So the first variable in my x vector is going to be, x vector is going to be C1. Okay. So C1, C2, C3, and so on. That's how my x vector is going to look. And let's see. So we have this as an n cross 1 vector. So this, and we have an additional variable cn plus 1. So we'll include that as well. So we'll have an additional variable here, which is because of the fictitious point that we had introduced, right? So this is an n plus 1 cross 1 vector, right? So A is going to have n plus 1 equations that we'll be including here. So A is going to be an n plus 1 cross n plus 1 vector matrix, and therefore B over here is going to be an n plus 1 cross 1 matrix vector, right? And the rows of A. So the rows of A are going to be coefficients of Ci. So let's say if I have Aij, so that means we are talking about the ith row and the jth column. So that implies we are talking about the coefficient of Ci in equation J, right? So hopefully that makes sense. Okay. So let's start with the first equation that we have, which is at I equals to 1. So at I equals to 1, this is the equation, right? So let's try to formulate our matrix. So this is the A matrix. So let's make a big matrix over here, right? Remember, rho represents the equation. And the column represents Ci. Okay. So this over here, for example, is going to be C1, C2, C3, and actually write closer over here. So C1, C2, C3, and so on. I might have written this wrongly. So Aij means ith row. So coefficient of Cj in equation I. That is what Aij represents. Okay. So let's now try to write the first equation in this form. So we see in my I equals to 1, the coefficient of C1 is minus 2d by delta z squared plus k, this, right, plus k. So that is there. Okay. Let's just make our lives a bit simpler. So we'll call d by delta z squared as alpha and v by delta z as beta. Okay. So I think there's a 2 over here. So v by 2 delta z would be beta, right? So that is what we'll be doing. This is also a 2. So this is also a 2 and this over here is also a 2. Okay. So therefore, this over here is minus 2 alpha plus k. Okay. And the coefficient of C2 in equation 1 over here is alpha minus beta, right? That is the coefficient. So that's alpha minus beta. Okay. And there are no other variables, C3, C4, nothing is there in my first equation, right? So that the problem for this, like the first equation is done, right? The second equation, let's see, the equation at I equals to 2 is going to be d C3 plus C1 minus 2C2 by delta z squared minus v C3 minus C1 by 2 delta z, okay, plus kC2 is equal to 0. That's the equation, which let's just club the coefficients together. So this is alpha minus beta C1 plus k minus 2 alpha C2 plus alpha minus beta. I think there's a plus over here. Alpha plus beta C1 and alpha minus beta C3, right? So that is how you write this equation over here, right? So I equals to 2 would have alpha plus beta here, okay? Then k minus 2 alpha here and alpha minus beta here. Okay. This is also k minus 2 alpha. Okay. So that is the case. And then it becomes fairly simple because this is just continued diagonally. So in the next equation, the coefficient of C2 becomes alpha plus beta. The coefficient of C3 is k minus 2 alpha. And the coefficient of C4 is going to be alpha minus beta, right? So you will see this kind of a matrix, this kind of a sparse matrix with just 3 diagonals, partially just the 3 diagonals being covered, except for at the boundaries, of course, but otherwise this kind of a matrix will be formed. And this kind of a matrix is called as a tri-diagonal matrix. Okay, this kind of a matrix is called a tri-diagonal matrix where you have 3 diagonals over here. Okay, so that is how you make a matrix, and this matrix will continue on till you reach the boundary over here. So once again, at n minus 1, let's see the last 2 equations as well. So if you write an equation for I equals to n minus 1 over here, that's going to be d Cn plus Cn minus plus Cn minus 2 minus 2Cn minus 1 over delta Z squared. Let's actually just write it for n because that holds as well. So let's do that. So I equals to n will have this d c n plus 1 plus cn minus 1 minus 2cn over delta z squared minus v cn plus 1 minus cn minus 1 over delta z plus kcn is equal to 0. I understand this is a bit challenging altogether as a lecture, but with some practice, I'm sure you'll be able to do such things very easily. So we'll be doing some problems. So hopefully you will be okay doing these things yourself. So let's go ahead. So this once again, Cn minus 1 has a coefficient of alpha plus beta. So that's alpha plus beta plus k minus 2 alpha Cn and plus alpha minus beta Cn plus 1, right? So the second last equation over here is going to be something like this with alpha plus beta here, k minus 2 alpha here, and alpha minus beta here, right? And the last equation that we formulated using the second boundary condition was that Cn plus 1 minus Cn minus 1 equals to 0. So all that you have here is Cn plus, so this over here is Cn minus 1, Cn, and Cn plus 1. So we have Cn plus 1 minus Cn minus 1 equals to 0, right? So that is the A matrix over here, okay? And the vector B, let's just write the vector B right ahead of the A matrix, right? So the vector B has all zeros except for the first equation, which was this right here, right? This was the first equation. So that's going to be minus alpha Ca naught minus beta Ca naught. So that is just minus alpha plus beta Ca naught, right? And everything else is 0 in the vector B, right? So altogether, this is not a very complicated problem for the computer to solve. This is a tri-diagonal matrix with a almost 0 B vector, right? So this can be very easily solved. And definitely this has a unique solution because you don't have the equation of the form Ax equal to 0 altogether. So you definitely have a unique solution for this kind of problem. But this is how you formulate this problem, this kind of problems. So definitely, as you see in such problems, coding would not be an issue. Definitely coding could be an issue because you have to sort of look for patterns over here, which we will discuss in as we start to code such problems. But the basic idea over here is to formulate this kind of a matrix. So once you're able to come up with this matrix, you will be able to solve half of the problem, right? So in most of these cases where you are trying to solve these complicated ODs, at least when you're starting to solve such complicated ODs, it is always a good idea to write everything down just the way we did, right? And using that, you will get a better idea on how to approach the code, how to write the code for yourself, right? But hopefully this was helpful. This might look challenging in the beginning, but I am very, very sure that as we practice more problems, you'll be very comfortable making a matrix of this kind. I remember when I learned this technique for the first time, I was just scratching my head. But once you start to get an idea, it becomes very simple. It becomes very obvious to you. So with more practice, with more tutorials that we'll solve, you will be very comfortable dealing with such problems. So a lot of our focus is going to be on how to formulate these matrices, and the especially the A matrix and the B vector over here, right? So the main focus is going to be on formulating these matrices, and then the next point comes on how to code such things, because there is definitely a pattern. So I think now you all are very good with identifying patterns, so that would not be a challenge, but formulating these matrices is definitely a challenge. So we'll do some tutorials with such problems, and we'll try to formulate matrices, and after that it is going to be easier to code for them. Okay. So next lecture would be a tutorial where we try to solve another ordinary. Perhaps we'll try to assign some values over here, and we'll try to code it out on Python. All right. Thank you.